Hello and welcome to the A-Level Chemistry Lecture Series. In this video, we're going to start with chapter 19.4, which is actually the last section of chapter 19. Now, in this particular section, we're going to look at two other enthalpy changes that can be associated with the lattice energy that we've been discussing this whole time. So let's get started. So the first of these enthalpy changes that can associate with lattice energy is the enthalpy change of solution. And this deals with the dissolving or solution of the lattice or the lattice of an ionic compound. When an ionic compound dissolves in water and it breaks up with those ionic bonds breaking and the ions separating, that enthalpy change, the energy change associated with that process, is called the enthalpy change of solution. The attractive forces in a lattice, when this happens, break apart. Those attractive forces being an ionic bond. So if we had, for example, just a lattice of positive or negative ions, those positive or negative ions are being attracted by an electrostatic force, otherwise known as magnetism. The positives attract the negatives attract the positives, and that's what causes ionic bonding. So these are held together through ionic bonds. Well, when an ionic compound dissolves, this lattice breaks, and those ionic bonds are going to kind of fall apart or break apart. That is the endothermic part of the process. Breaking bonds is always endothermic. Now, that energy needs to be overcome somehow, and we're going to talk about how exactly it's overcome in a little bit. But before we go into that, let's talk about the definition of standard enthalpy change of solution. When an ionic solid dissolves in water and makes a solution, that's when the enthalpy change of solution comes in, which is particularly described as the energy absorbed or released, or we can just say the enthalpy change, when 1 mole of an ionic compound, or 1 mole of an ionic solid more specifically, dissolves in sufficient water to form a very dilute solution under standard conditions. So the part that mostly throws people off here is not the 1 mole of an ionic solid. I think we are at this point comfortable with the idea that enthalpy changes are associated with 1 mole of something, in this case an ionic solid, or the fact that it dissolves because it's the enthalpy change of solution, but this part, insufficient water to form a very dilute solution. So let's talk about this right now. So what this essentially means is that when we're talking about the enthalpy change of solution, the molarity of the solution we're making has to be low. The reason why is that if we have a really high molarity, those ions are going to start interacting with each other in the solution, and it can actually mess with the enthalpy change of solution. So when we're doing this, we're essentially saying that we're dissolving 1 mole of an ionic solid in a lot of water, in a large amount of water, in order to make a solution that is very dilute and not concentrated. So this is necessary because if it's concentrated again, that will change the energy absorbed or released, or the enthalpy change, and so it wouldn't be enthalpy change of solution anymore. So make sure that when you're doing this definition, you include that insufficient water to form a very dilute solution in your definition. Now, enthalpy change of solution could be positive or negative. Unlike some of the other ones we see like atomization or lattice energy, depending on the specific compound, the enthalpy change of solution could be either endothermic or exothermic. The substance is only going to be soluble in water, however, if the value of the enthalpy change of solution is negative or has a very small value. So, soluble, that term that we've used since honors chemistry, is only going to be applicable when delta H of solution is either negative or has a very small positive value. Why? Because in order for something to dissolve, it needs to overcome the enthalpy change of solution. So if the enthalpy change of solution is negative, it's exothermic, great, there's nothing to overcome, energy is released. Or if it has a very small positive value, ambient energy, the energy of the environment, can be used in order to overcome the enthalpy change solution. But when delta H of solution is large, very large, then a compound is said to be insoluble. A compound is insoluble when delta H of solution is extremely large. So positive and large. And that's because if the endothermic process of dissolving is too high, if it requires too much energy to dissolve a compound, then we just can't use ambient energy to do that. We're going to have to heat it up or something along those lines. Now, the terms soluble and insoluble are relative. They are something that we use to generalize, but in reality, every salt, every ionic compound dissolves to some extent. It's just that if the dissolving happens to a very, very, very small amount, we essentially said it's insoluble. For example, if we added 1 mole of a substance to a solution and only 0.00001 moles of it actually dissolved, then for all practical purposes, that substance is insoluble. So that's why these are relative. There is a limit to either solubility or insolubility. Everything dissolves to some amount, and nothing dissolves exponentially forever, right? There is going to be reach a threshold where things will stop dissolving, even if they're extremely soluble. So delta H of solution, like any other enthalpy changes, can be represented by an equation, but this particular equation has a nuance about it. We need to keep in mind something very specific, and that's a use of AQ. When we're talking about the enthalpy change of solution, we're talking about dissolving something. When we talk about dissolving something in an equation, we're not going to use water as the thing that's dissolvent. Or at least we're not going to use H2O. Why? The term H2O, if we were to grab an equation and put in it plus H2O, what this means is reacts with water. If we say plus H2O in a chemical equation, we're saying something is reacting with water. Instead, we use the term AQ to mean a large amount of water, meaning that it is being dissolved in water. So we use AQ in an equation when we want to say that something is being dissolved in water, and we use H2O in an equation when we want to say that something is reacting with water. So if we wanted to do the enthalpy change of solution, delta H sol, standard, of magnesium chloride, for example, MgCl2, we will say that MgCl2 solid plus AQ, meaning that it's going to dissolve in a large amount of water, is going to give us MgCl2 aqueous. Now, thinking back of what we learned in honors chemistry, remember that when we say something's aqueous, and specifically an ionic compound, we are saying it is dividing up into its ions. So another way of saying this will be with the same beginning, MgCl2 solid plus AQ, yields not MgCl2 aqueous, but the separated ions because of the dissolution process. So not MgCl2 aqueous, but Mg2 plus aqueous, the ion of magnesium, plus 2Cl minus aqueous, the 2 ions of the chloride here. These are both going to be the enthalpy change of solution of magnesium chloride, which just happens to be negative 55 kilojoules per mole, meaning that magnesium chloride is soluble in water. So that's the enthalpy change of solution. It is a bit of a nuance when writing these equations because of that AQ. It is not an equation of a chemical process. Instead, it is an equation of essentially a physical process of something dissolving. And so we don't use H2O like we will use in a reaction with water. We use AQ to symbolize that it's dissolving in water. So remember the definition of enthalpy change of solution. Remember that it could be negative or positive depending on the compound, and we'll see a few of different examples, and we're going to discuss why in the next slide, and learn how to write these equations using AQ to symbolize the water that's doing the dissolving, the solvent. Let's move on. So what exactly happens when an ionic compound dissolves? Because this is very key to why enthalpy change of solution could be either positive or negative. When an ionic compound dissolves, essentially the ionic bonds are going to break. So when we have the ionic lattice here and a compound starts dissolving, the ionic bonds between the ions break. Now the process of ionic bonds breaking is endothermic. Because bond breaking, as we learned in AICE chemistry, is endothermic. It requires energy to break bonds. So when this ionic crystal starts breaking, ionic bonds break, an endothermic process happens. Well, what's doing the breaking apart of the ionic crystal is water molecules. And if we remember, water molecules are polar. They have a partial positive and a partial negative end. So with water, hydrogen is partially negative and oxygen is partially positive. Well, that's why water interacts with the ionic compounds. The partial negative oxygen is going to be attracted to the positive ions in the lattice. The partial positive hydrogen is going to be attracted to the negative ions in the lattice. And they're going to essentially kidnap these ions. They're going to break them apart. And then water is going to surround the ions, either with the oxygen pointing in if it's positive ion, or the hydrogen pointing if it's a negative ion, in a process called solvation. So, and this is something that we studied back in honors chemistry, really. But solvation is a process of the water molecules surrounding that ion. And the reason why solvation happens is because of something called ion-dipole forces or ion-dipole bonds, depending on who you ask and where you're asking. But solvation occurs because ion-dipole bonds form between the charged ions and the partial positive and partial negative sides or poles of the water molecule. Essentially, when the water molecule is attracted to that ion, that attraction actually creates an interactive force. Just like intermolecular forces or bonds are magnetic attractions, this attraction between a pole of water, so the partial negative to a positive ion, or the partial positive hydrogen to the negative ion, are forces of attraction. Those forces of attraction are called ion-dipole bonds. As you probably remember from AICE chemistry, when a bond is formed, or when an intermolecular force or any kind of force of attraction is formed, energy is released. Bond formation is exothermic. So in this process, ion-dipole bonds or forces form. The process of ion-dipole forces forming is exothermic. So you have two opposing processes here. You have the breaking of the ionic bonds in the lattice, which is an endothermic process, and then the water molecules that are doing the dissolving of the ionic compound are going to form ion-dipole bonds between the polar molecules of water and the ions, which is an exothermic process because we're creating a force of attraction. So if we look at this, we have endothermic on one side, or endothermic process to begin with, and then an exothermic process to end it. Whether an enthalpy change of solution is endothermic or exothermic depends on which of these two processes is larger. So if we have, or we need more energy to break the ionic bonds, the ion-dipole bonds release when they formed, then we have an endothermic process. If the amount of energy released by the ion-dipole bonds forming is greater than the amount of energy needed to break the lattice, the ionic bonds in the lattice, then we have an exothermic process. So it's really just a matter of a bit of a balancing act, right? So again, here, I'm going to kind of make a little graph or chart here. If the energy needed to break bonds is larger, so ionic bonds break. So if the ionic bond, the amount of energy needed to break the ionic bonds is larger than the amount of energy released by ion-dipole bonds forming, then in this particular case, that solution that dissolving is going to be endothermic. And it just occurs to me that I probably should have used the opposite colors, but so this is going to be endothermic because more energy is needed for the endothermic process than the energy released by the exothermic process. On the other hand, if less energy is needed to break ionic bonds than the amount of energy released by the formation of ion-dipole bonds, then because more energy is being released, this process will be, or this dissolving will be exothermic. Because again, formation of ion-dipole bonds is negative delta H, it's an exothermic process, whereas the breaking of the ionic bonds, it is an endothermic process. It is positive in charge. So whether the process is endothermic, meaning delta H is positive, delta H of solution is positive, or whether that process is exothermic, meaning the enthalpy change of solution is negative, will depend on these two factors. All right? So let's now discuss the other enthalpy change, which is enthalpy change of hydration. Enthalpy change of hydration is related to enthalpy change of solution, and it's actually more like a part of it. The enthalpy change of hydration is the enthalpy change associated only with the process of ion-dipole formation. The official definition for the standard enthalpy change of hydration, delta H standard hyd, is the enthalpy change when 1 mole of a specified gaseous ion dissolved in sufficient water to form a very dilute solution under standard conditions. So what is the enthalpy change of hydration? The enthalpy change of hydration is essentially the enthalpy change for the ion-dipole process. It grabs an ion, either positive or negative, in the gaseous state and turns it to that same ion, either positive or negative, in the aqueous state. So essentially, it's like the enthalpy, the lattice energy, but for specific ions. In the sense that we're grabbing the ion in the gas state and we are going to dissolve it. We're going to put it in water to form those ion-dipole forces that we talked about. So there's no bond breaking here. The ion-dipole bond formation is really the only kind of interaction that enthalpy changes of hydration are going to have. The ion is already ionic. It's already a single standalone particle, and it's in the gas state. So there's no bonds to break. There is no change of state of matter to do. It is just grabbing that ion, putting it in water, and having those ion-dipole bonds form between the water and the ion. Because of this, the enthalpy change of hydration can be represented by an equation that also uses the aqueous as a component. just like the lattice energy did. Sorry, so just as the enthalpy change of solution did. So, when we grab this ion, so we'll use calcium for example, we can have the calcium ion in the gas state react with aqueous, which again means enough water to form a solution, so not reacting with water, but dissolving in it. So the ion in the gas state dissolves in water and forms the aqueous ion. So notice the enthalpy change of hydration of calcium, for example, is negative 1650. Chlorine, or the chloride ion, should I say, because it's for ions, in the gas state can react with aqueous with enough water. So we put the ion in the gas state in water, and it creates ion-dipole bonds between the chloride ion and the water to form aqueous chloride. The enthalpy change of hydration of that is roughly negative 364 kilojoules per mole. Because it's only going to deal with bond creation or bond formation, right? Because, let me change this. So because ion-dipole formation is creating attractions, there is no breaking of bonds. And because the forming of attractions, bonds, intermolecular forces is always going to be exothermic or negative, then the enthalpy change of hydration is always exothermic, because it only deals with the one exothermic process of the formation of the ion-dipole forces. So what is going to affect the size of the enthalpy change of hydration? Because notice, the calcium enthalpy change of hydration is negative 1650, whereas the chloride one is only negative 364. So why is this the case? There are two things that are going to affect the enthalpy change of hydration of a specific ion. That is the size of the ion and the charge of the ion. So same exact things that always affect everything for ions: size and charge. Larger ions with larger charges are going to have larger densities and therefore larger enthalpy changes of hydration. Smaller ions with smaller radius are going to have higher charge densities and therefore higher enthalpy changes of hydrations. So to put this all in a little neat summary, if we have a large charge and a small size for an ion, that's going to yield a large charge density, as we talked about earlier or in prior sections. And if we have a large charge density, that means that the bonds formed between the ion and water are going to be very strong, and so we're going to have a very large, or very negative, shall we say, delta H of hydration. So the larger the charge, and the smaller the size, the larger the charge density, and therefore the larger or more exothermic, more negative, the enthalpy change of hydration will be. And we can see that here. Chlorine is bigger. Actually, chlorine is bigger than the calcium ion, and it has a -1 charge. Whereas the calcium ion is smaller and it has a +2 charge. So larger charge, smaller size, larger enthalpy change of hydration, versus bigger size and smaller charge, smaller enthalpy change of hydration. So keep these things in mind, because you will be asked to compare the enthalpy change of hydration of different ions and to use both the charge and the size as an explanation. Now, as you can guess, because these are all related to each other, enthalpy change of hydration, enthalpy change of solution, and lattice energy can actually be put into a Born-Haber cycle, or a enthalpy cycle, Hess cycle, whatever you want to call them, where you can relate enthalpy change of solution, enthalpy change of hydration, and lattice energy through a cycle that we have here. Keep in mind that the enthalpy change of solution and the enthalpy change of the lattice will be for compounds, whereas the enthalpy change of hydration that we just talked about are for individual ions. So you might have to use multiple enthalpy change of hydration because you have multiple ions in an ionic compound. And this could also be turned into an enthalpy change of, an energy level diagram as well. And we'll talk about what that looks like in when we do the practice question. So, what is this Hess cycle? What is this enthalpy change cycle? Well, when we look at the relationship between the enthalpy change of hydration, the enthalpy change of solution, and the lattice energy. First of all, we'll start at the top with lattice energy because that's the main focus of this chapter. The lattice energy for a compound is going to be going from the gaseous ions to the ionic solid. So that is always the case. That's the definition we learned earlier in section 1. It's going from the gaseous ions to the ionic solid. That's enthalpy change of lattice energy. When we look at the definition of the enthalpy change of solution that we saw earlier in this section, the definition says when an ionic solid, right, so we're starting here, an ionic solid is dissolved in enough water to create a very dilute solution. Well, solution of ionic solids are going to be the ions in aqueous solution. So if we point this arrow down, we have here the enthalpy change of solution of the same compound that we have the enthalpy change of the lattice energy for. On the other hand, if we start at the other side, the enthalpy change of hydration that we just saw is when gaseous ions are dissolved in enough water to make a very dilute solution. So again, we're going from the gaseous ions, in this case, instead of the ionic solid, to the ions in the aqueous solution. So again, this one points down as well. So here we're combining the three definitions into one Hess cycle. If we then look at the arrows, we have two arrows that match in direction and one that disagrees. So if we look at these arrows, the arrow for lattice energy and the arrow for enthalpy change solution agree in the direction that they're facing. Whereas if I keep going, the enthalpy change of hydration arrow is going to disagree. It's going to go the opposite way. So if we wanted to make an equation out of this Hess cycle, we will again create our alternate path arrow. So we have on one side the disagreement arrow, which is the enthalpy change of hydration, is equal to the two arrows that do agree, which are the enthalpy change of the lattice plus the enthalpy change of solution. So this plus this is equal to this. Now do keep in mind that the enthalpy change of hydration is going to be for multiple ions, whereas the enthalpy change lattice and solution are going to be for ionic compounds in general. So if we were doing, let's say, magnesium chloride, like we did or like we saw earlier in the examples, the enthalpy change of lattice will be the enthalpy change of lattice for magnesium chloride. The enthalpy change of solution will be the enthalpy change of solution for magnesium chloride. But the enthalpy change of hydration will be the enthalpy change of hydration for the magnesium ion and the enthalpy change of hydration for the chloride ion separately. And and if you're visualizing this, you can actually say two types of chloride ion because you're going to have two chlorines in that compound. So this is something to keep in mind. Whereas we're just writing as the enthalpy change of hydration, there's actually going to be at least two enthalpy changes of hydration involved in these Haber cycles or Hess cycles. So enough chatting of the conceptual. Let's look at a practice problem. So let's take this question as an example, right? Here we have a question that says, use the data in table 1.1 to calculate the enthalpy change of solution. So we're looking for enthalpy change of solution of potassium iodide. So this is going to be delta H sol delta H solution for potassium iodide, Ki. And then we're given three different enthalpy changes, but we're not told what the enthalpy change is. Instead, we're given the equations for them. So this is one of the reasons why it's important for us to learn how to read these equations. First, we have the enthalpy change when potassium ions in the gas state and iodide ions in the gas state react with each other to form the solid ionic compound potassium iodide. Remember, that's the definition of lattice energy. Gaseous ions create solid ionic compound. So this first one is going to be the enthalpy change for the lattice for potassium iodide. So notice, both the lattice enthalpy change and the solution enthalpy change are for the compound we're working with, which is potassium iodide. On the other hand, let's look at the other two enthalpy changes. Here we have the enthalpy change when the potassium ion in the gas state reacts with the potassium, or reacts to make the potassium ion in the aqueous solution. So we're from the gaseous ion to the aqueous ion. So this will be enthalpy change of hydration. But remember, the enthalpy change of hydration are not for compounds, they're for ions. So this is the enthalpy change of hydration of the K plus ion. On the other hand, the other enthalpy change here, the one we have all the way at the bottom, and let me do this in orange, is the enthalpy change when iodide ions in the gas state turn into the iodide ions in the aqueous state. So again, we're going from the ion gas to the ion aqueous. So this is still enthalpy change of hydration, but this is the enthalpy change of hydration of the iodide ion, the negative ion, the anion in the compound. So let's make, and we can draw this as both an enthalpy cycle and an energy level diagram, and let's do both of them before we actually get the answer. So if we try to create the Hess cycle, the Born-Haber cycle, if we start always at the top for the Born-Haber cycles of lattice energy, we're going to start with the lattice energy, right? So at the very top, we're going to start with the ions in the gas state, like the lattice energy has. So we're going to start with K plus gas plus, that's ugly, plus I minus gas. And that's going to create, and we're going to put it in red to use the same colors. So, and that's going to create the solid ionic compound. So Ki solid. So this right here, the ions in the gas state creating the solid ionic compound, is going to be the enthalpy change lattice, the lattice energy of the compound Ki. Now the other part, the third part of our triangle, we're creating a Hess cycle here for lattice energies. In the bottom is going to be the ions again, but not in the gas state. These are going to be the ions in the aqueous state. AQ, so K plus AQ plus K, I minus AQ. So here we have the potassium ion and the iodide ion, but unlike here in the top left, we have them in the aqueous state. Now let's talk about enthalpy changes, because when we convert from potassium iodide solid, from the solid ionic compound, to the ions in aqueous solution, we're talking about here is dissolving them. Remember, ionic compounds, when they dissolve, dissociate into their ions. So when we go from the potassium iodide in the solid state, the ionic compound in the solid state, to the ions in aqueous solution, we are going to talk about the enthalpy change of solution, specifically here the enthalpy change of solution of potassium iodide. On the other side, when we're talking about going from the ions in the gas state to the ions in the aqueous state, we are talking about dissolving each individual ion. Remember, when we're talking about hydration, going from the gaseous ions to the aqueous ions, We are talking about individual enthalpy changes for each individual ion. So we have the enthalpy change when potassium plus gas, changes into potassium plus aqueous. That's the enthalpy change of hydration of the potassium ion. And then separately, we also have the enthalpy change when the iodide ion changes into the iodide ion in the aqueous state, so from gas to aqueous. And that's why the enthalpy change of hydration, but in this case of the iodide ion. So we have to add both of these up. So that's our Hess cycle. When we form our alternate path here, and we'll do it here in rainbow, we have these two paths, the red and purple arrows, agreeing in direction, meaning that delta H lat and delta H sol are going to be added to each other. So we're going to have delta H lattice of Ki plus delta H of solution of Ki, which is in purple, is going to be equal to the other side of this path, right? To the other alternate path. So this is going to be equal to this side, the side that disagrees with their direction. And that's going to be the enthalpy change of hydration of, in this case, potassium ions. And if it was K2, for example, we'll have 2 potassium ions, we'll multiply this by 2, but that's not the case here. And then the enthalpy change of hydration, put the plus sign, so plus the enthalpy change of hydration of the iodide ion, delta H hydration for I minus. So that's our equation. Now, the question specifically asks us for the enthalpy change of solution. So all we have to do here is rearrange this equation so that we isolate the enthalpy change of solution. So we have delta H sol of Ki is going to be equal to the enthalpy change of hydration, delta H hydration of K plus the enthalpy change of hydration of I minus because we gotta put this enthalpy change of lattice on the other side, minus the enthalpy change lattice for Ki. And now we can just plug the numbers in from the equation and get our answer, which in this case will be that the enthalpy change of solution, delta H solution of Ki, is going to be equal to the hydration enthalpy change, which is, we have here negative 322. Oops, that's not a nice 2. 322 plus the enthalpy change of hydration of iodide, which is, according to this, negative 293. So plus negative 293 minus the enthalpy change for the lattice, which is, according to this, negative 629. So minus negative 629. Notice how I kept the minus and the negative on the 629 separate. That way when I do my math, I can follow it fairly accurately. So I can do minus and negative instead of doing plus and then messing something up by accident. And that should give me the enthalpy change of solution for Ki, which we have negative 322 plus negative 293 plus, or minus, sorry, negative 629, which should be equal to 14 kilojoules per mole, roughly. And this will be positive. You don't need to put the plus sign, but it does sometimes help to put that plus sign there. All right, so that's all from the Hess cycle. So how would this look like if it was an energy level diagram? Well, if this is an energy level diagram, we have to realize something. Most of these are negative, so we're going to have mostly exothermic reactions. And if we think of everything we have, the gaseous ions, the aqueous ions, and the lattice, the thing with the most potential energy, the thing that's going to be highest up on this energy level diagram, is going to be our gaseous ions. So we're going to put them all the way at the top. This is simply because gas state is going to be really high in energy, so it's going to be really high up on this potential scale. And also ions, which are positive and negatively charged when they're separated, are also going to be really high in potential energy because they can attract, they want to attract to each other. So the very top of this, we have our gaseous ions and, well, just our gaseous potassium ion and our gaseous iodine ion. All the way at the bottom, the most stable thing we have here is what we normally have in nature, the solid potassium iodide. So we can start there because if we know the highest thing is the gaseous ions and the lowest thing is the solid potassium iodide, then we can already draw one of the arrows, which is the lattice energy. So right here, going from the gaseous ions to the potassium iodide solid, that's going to be the delta H lattice of Ki. On the other hand, the other things that we're going to have are the lattice, the hydrations, and the solution. Well, if we're starting at the gaseous ions, solution starts from the solid, going to the aqueous ions. So starting here, this cannot be solution because solution does not involve the gaseous ions. So what we're going to have here on the right, or sorry, on the left, is going to be our hydrations, both of them. Now, both of these are negative charges, or negative enthalpy changes, so they're going to be pointing down as well, just like our lattice energy is, which is also negative. So we're going to have here our enthalpy change for, our enthalpy change for the hydration. So delta H hydration. First, we'll do iodine. It doesn't really matter which one we do first. We can do either iodine first or potassium first. And so when we get that level, that's going to be that's still the K plus gas, because what hydration means is that we turned the iodine, in this case, because we're doing the iodine, from that I minus gas to I minus aqueous. And then once we do hydration, we can then also do the potassium, which is slightly bigger, right? We look at the numbers. So the arrows are going to be slightly bigger. And these arrows aren't, I'm not drawing them to scale very well, but you know, what matters is the size is bigger. And then when we go from potassium now, when we hydrate potassium, so when we do the delta H of hydration for K plus, what we're going to have here is we're going to turn that K plus gas to K plus aqueous. Oops, this should be black. So we're going to be turning that to K plus aqueous. And then we had already turned the iodide to I minus aqueous. So now we have that, then we only have one gap here. And that gap is going to correspond to our final enthalpy change, which is the enthalpy change of solution. So the enthalpy change of solution, as we saw, is actually positive in charge, positive 14. So this one being endothermic is going to point up, and that's going to be delta H of solution, which is going to turn our iodide solid to K plus aqueous plus I minus aqueous. So that's it. That's what an energy level diagram looks like for this same Hess cycle. So as we have discussed in section 3, we can turn really any Hess cycle into an energy level diagram. It's just a matter of putting the right pieces in the right places. And looking at the sizes. So one of the things that kind of keyed me into the fact that the lattice energy was going to be by itself here is the size. Look at how big the enthalpy change for lattice energy is compared to the ones for hydration. When you add these two up, they kind of almost equal this one. And so that kind of keys us into them being in different places, with that difference between them being 14 being the enthalpy change of solution that we have to add to the left side. All right, so that's how we draw an energy level diagram for this same Hess cycle. It doesn't matter which one you do, whether you draw this as an energy level diagram or as a Hess cycle, because in this particular question they're not asking for either, they're just asking for the math. The math is going to end up being the same here. You're going to end up with the exact same math, and so you're going to end up with, if again we follow the arrows, we can see here how, let me make this a little bigger, how this right here, if we follow this alternate path, these two agree, so we are going to add these two up, the solution plus the lattice is going to end up in equal to the oppositely path arrows, which are these two, coming in a different direction. So these two are going to be equal to each other, which we have, or we're going to be on the same side of the equal sign, which we have right here. Oh, let me make that a little more even. So we have that right here. And then the other two, which are agreeing in direction, are going to be on the other side of the equal sign, which is right here. And so from there, the math is just exactly the same. We put everything in its rightful place, plug in the numbers, and we'll get plus 14 in either case. All right, so that's how we tackle a question like this about lattice energy, hydration, and solubility using the Hess cycles. And we can see here, this is a 1-point question. This is the mark scheme. It's just simply they're grading your math and whether you can get the right answer. Now, do you need to draw the Hess cycle? Do you need to draw the lattice, the energy level diagram for this? No, as long as you remember this equation, the hydration enthalpy changes are going to be equal to the lattice plus the solution enthalpy changes. You can just use the equation instead of the Hess cycles in order to answer this question. Obviously, because the answer to this is just a calculate question, talking about command words, we're not being asked to draw a Hess cycle, we're not being asked to any specifics. So let's keep going, because this can now apply to other things. Let's talk about how these enthalpy changes can apply to something like solubility, right? Because we talked about enthalpy change of solution, and we talked about how enthalpy change of solution relates to whether something is soluble or not. Remember that we said earlier that if an enthalpy change of solution is, so if delta H of solution is negative or a small positive, that's what I mean that that compound is soluble. Where instead, if the enthalpy change of solution, delta H of solution, is very big and positive, then that's what I mean that that compound is insoluble. And this applies to the solubility trends that we learn in AS chemistry. For example, in AS chemistry, we learned that group 2 sulfates are going to get less soluble, their solubility decreases as we go down the group. Meaning that magnesium is going to be magnesium sulfate is going to be a lot more soluble than something like barium sulfate. And calcium sulfate is going to be less soluble than magnesium sulfate. As we go down, their solubility decreases. And we can see that in the numbers. Solubility of magnesium sulfate is 1.83 moles per cubic decimeter. That means for every 1 mole of solution, 1 mole or 1.83 moles of magnesium sulfate dissolve. If we compare that to barium sulfate, for every 1 liter of solution, 1 cubic decimeter solution, 9.43 times 10 to a negative 6 moles of barium sulfate dissolve, or 0.0000943. That's a much smaller number than 1.83, right? A lot less moles of barium sulfate dissolve in 1 liter of water than magnesium sulfate. With all solubilities, this is dictated by their enthalpy change of hydration and lattice energy. Why? The equation that we just learned for enthalpy changes of solution, delta H of solution, is that enthalpy change of solution plus enthalpy change of lattice is equal to enthalpy change of hydration. So if we rearrange this equation to isolate solution, we get that the enthalpy change of solution is equal to the enthalpy change of hydration of the ions minus enthalpy change of the lattice energy. So what does this mean? That means that the enthalpy change of solution, and therefore the solubility of a compound, is dependent on two things. It's going to be dependent on the enthalpy change of hydration and the lattice enthalpy change, the lattice energy enthalpy change. So how exactly do hydration and lattice energy affect? Now, this is an extremely common question in paper 4 for A-level chemistry. And you have to pay attention, because anytime you're asked to explain the solubility of something, like group 2 sulfates, and they won't ask you based on anything. They just say explain the solubility of group 2 sulfates and the trend. Whenever you ask that question, you want to explain that based on thermodynamics. We want to explain that based on enthalpy changes. So we need to pay close attention to these next few slides. So what factors affect the solubility of group 2 sulfates, and really of any compound, any ionic compound solubility? Hydration enthalpy and lattice energy are the two factors. So let's start with each, and I'm going to rewrite here the equation at the top. We said that enthalpy change, oops, that is way too big. So we said that enthalpy change of solution, which guides solubility, is equal to the enthalpy change of hydration minus the enthalpy change for the lattice energy. So let's start with hydration, right? I'm going to underline this in green since the slide is green here. So let's start with hydration. Enthalpy change of hydration for group 2 ions decreases or gets less exothermic down the group. So as we go down the group, the hydration is going to decrease. And it's actually, that's very fast. Why? The hydration enthalpies are individually per ion. This is due to the ion size of the ions of the group 2 elements increasing down the group, and therefore decreasing charge density. When we go from magnesium 2+, to calcium 2+, and then eventually all the way down to barium 2+. Which one did I miss? Strontium. So let me put barium where it belongs. So then strontium 2+, and then eventually to barium 2+. What happens to the ions? The charge stays the same. They're all 2+ in charge. However, the size increases. Down the group, the size of the ions increases, but because the charge stays the same, that means that charge density decreases. As the ion gets larger, the charge density goes down. Because charge density goes down, the forces that attract the polar water to the ions are going to be weaker, and therefore the enthalpy change of hydration decreases. So as we go down the group, this actually happens fairly quickly. The enthalpy change of hydration of magnesium 2+ is much larger, that's why we have 2 greater than signs, than the one for calcium. And the enthalpy change of calcium 2+ is much larger than the one for strontium. The enthalpy change of barium 2+ is much larger than barium. Because enthalpy change of hydration is based on individual ions, the effect that this change in charge density has on the enthalpy change of hydration is huge. And so the decreasing happens very, very quickly. So we can say it decreases rapidly. We'll put 3 arrows to show that. On the other hand, if we go to the lattice energy, and I'll put this in pink, I don't have purple, but I'll put this in pink. So if we talk about lattice energy of group 2 ions decreases down the group as well. Why? Essentially, enthalpy change of hydration and lattice energies are affected by the same things: ion size and ion charge. So as we go down, the size of the ions increases and the charge density decreases. However, whereas the enthalpy change of hydration is based on one ion, and let me put this in green again. So whereas the enthalpy change of hydration is based on one ion, the enthalpy change for the lattice energy is going to be based on both ions. So it does decrease. The lattice energy does decrease for the exact same reason that the hydration enthalpy decreases. However, because we're looking at group 2 sulfates, the change is going to be a lot milder. The reason being that sulfate is still there, and for every single one of these group 2 sulfates, the sulfate ion is still the same in all of them. Because the sulfate ion is so large, it's going to damper the effect of the cation. Essentially, the sulfate ion has a much larger influence on the lattice energy than the group 2 ions do. And since every single one of these compounds has sulfate in it, they stay relatively constant and only decrease by a little bit because of the changes in the cation. So what happens? In the lattice energy, there is still a decrease down the group as we go from magnesium sulfate to calcium sulfate to strontium sulfate, because remember, all of these have SO4 associated with them. And because we all have SO4 associated with them, and because SO4 is such an influential large ion, the decrease that we see is very small, as denoted by only one greater than sign. So what happens? And lattice energy does decrease as we go down the group, but it decreases only by a little. We'll only put one arrow here. So we are doing hydration minus lattice energy. So what, in order to get the solution. So what happens? As the hydration decreases at a much faster rate than the lattice energy, what's going to happen is that this number gets smaller much quicker than this number does. So let's look at what that means for our solution. We know that the enthalpy change of hydration is going to decrease down the group very drastically, and it's going to do so a lot more drastically than the lattice energy. Let me put up the equation again, just so you have it in front of you. So enthalpy change of solution is equal to enthalpy change of hydration of the ions minus the lattice energy. So again, we said that this right here, the enthalpy change of hydration, decreases much more quickly. So we'll put 3 arrows than the enthalpy change for the lattice, which also decreases but less rapidly. That means that because the enthalpy change of hydration decreases much more rapidly than the enthalpy change for the lattice, the enthalpy change of solution gets more endothermic down the group. And that's because the hydration decreases faster than the lattice does, causing the enthalpy change of solution to become more positive as we go down the group. Now, this can be very hard to think about because, remember, when we say decreases, we mean gets less negative. So what happens to the enthalpy change of solution? What you need to know is that it gets more positive, or we can say it increases essentially, as we go down the group, because this negative number, because remember the lattice energy is negative, is decreasing less rapidly. And when we subtract the negative, we get a more positive number. Because remember, hydration is always going to be, let me put this in green. Hydration, as we talked about earlier, is always going to be exothermic, it's always going to be negative. And lattice energy is always going to be negative as well. But because we're subtracting a negative, we're essentially adding to the hydration. Because this number gets smaller less quickly than this number, the essentially positive part of this equation, because minus and negative will be a positive, the positive part of the equation, the negative delta H, is not changing as drastically, making the enthalpy change of solution more positive. Because compounds with more endothermic delta H solutions are less soluble, we are going to get less soluble as we get down the group. Because this gets more endothermic, and the more positive the enthalpy change of solution is, the more insoluble a compound is, then as we go down the group, the compound is less soluble. This is the thermodynamics explanation as to why group 2 sulfates get less soluble down the group. They get less soluble down the group because their enthalpy change of solution gets more positive. Why does it get more positive? Because the lattice energy changes less drastically or decreases less drastically than the hydration of the ions. And the reason for that is that the lattice energy is dependent on both the group 2 ion and the sulfate, whereas the hydration is only dependent on the group 2 ion. And as we go down the group, ions get larger, charge density gets smaller. And we can see that here visually, right? Because this is the enthalpy cycle or the energy level diagram for calcium sulfate. This is the one for strontium sulfate. Notice that the enthalpy change of solution for strontium sulfate is much larger, much more positive than the one for calcium sulfate because it's lower down. Why is that the case? Notice that its enthalpy change of hydrations are much smaller than the ones for calcium sulfate. And that the lattice energy for calcium sulfate remains much larger than the one for strontium sulfate. All right? So that's the thermodynamics explanation for this. This is probably one of the trickiest parts of this chapter, being able to explain this, because explaining things is difficult. So make sure that you understand this thoroughly and make sure that you are able to at least draw some kind of mind map to build your explanation. All right. So what do we mean by a mind map? Let me bring this up. So what would a mind map essentially look like? Mind map is essentially being able to map out your answer before you write it. So at the very top, we have obviously our main idea we want to get through. Main idea we want to get through is that group 2 sulfates get less soluble due to more positive delta H of solution. That's your first step, right? Because delta H of solution being more positive directly explains why they're less soluble. After that, what do we want to explain? We want to explain why delta H of solution gets more positive. Delta H of solution gets more positive because, I'm going to put BC here because delta H of hydration decreases more quickly than delta H lattice. And then we might be able to put the equation in there, right? The equation being the delta H of solution is equal to delta H of hydration minus delta H lattice. And then you kind of want to keep this trend. You got to explaining parts that you just brought up. So we brought up delta H of solution to explain solubility. Why they become less soluble? Because delta H solution becomes more positive. So now we're going to explain this. Why does delta H of solution get more positive? It gets more positive because delta H of hydration decreases more quickly than delta H of lattice. And then this is the equation. That's why it's important. Okay, why does this happen? This happens because delta H lattice depends on both the group 2 ion and sulfate ion, but delta H of hydration only depends on the group 2 ion. So that's what affects this. Why the explanation for that difference. And then you can explain, okay, why do the group 2 ions matter? Going down the group. Oops, down. Group 2. Ions get larger, which means that charge density, so I'm going to put a slash here, charge density gets smaller. And that explains why it's important that they depend on group 2. That, and then maybe here as an aside, because we also got to explain sulfate, SO4 2 minus is large and outweighs the group 2 ions. So this is mind mapping your answers, right? For explanation questions, this is very useful because now we have a bit of a structure of how we're going to answer that question. Is this something that's absolutely necessary? No, it's not absolutely necessary for you to do, but it helps you build the structure of a question before you start writing your paragraph. And it helps you understand all the different points that you could be making. And realistically speaking, this is anywhere, if this was only a 2-point question or a 1-point question, I would just explain this. If it was a 2-point question, I would add this. If it was a 3-point question, I would add this level, which includes both of these, right? So it helps you kind of plan out your marks. And that's it. That's how we explain this. So make sure you have a really good grasp on this explanation and that you're able to then build a form of mind map to answer your question. Do you need to include as many words as I did here? No, I'm teaching. That's why I did this. Make sure you just put short words to remind you. So more positive delta H sol in the top. You don't need to write all of this. Next, delta H hydration changes quicker, delta H lattice. Just put short words to kind of help you guide yourself when you're writing the explanation. All right? Well, that's it for this section and for chapter 19. I will see you all in the next video.